So this is Linear Algebra Lecture 12, and we are studying eigenvalues and eigenvectors. So we have V is a finite dimensional vector space, and T from V to V is a linear operator. That means a linear transformation from a vector space to itself. And the idea is to try to understand this operator T and maybe to break it down into simpler pieces. So if you imagine this is the vector space V, you might have a subset W, or a subspace even, where for every vector, so we say W is T invariant. Let's say W is a subset of V. W is T invariant or invariant under T. They mean the same thing if T of W is in the set W for all vectors W in the set W. So if you take any vector W in W, it gets mapped to something W inside the same set. So then T restricted to W maps or sends, if you like, whatever word you like for a function, W into W. And we often like to look at subspaces W. So we say T is a T invariant subspace, or a subspace invariant under T if the space maps, if the operator sends W into W. And the simplest invariant subspaces, if they exist, they don't always exist, are one-dimensional. So if W is a subspace of dimension 1, then W is generated by a non-zero vector called little w, and so W is just the set of all scalar multiples CW. C in the field. Let's say we're working over the reals. A one-dimensional subspace is just all scalar multiples of some non-zero vector. And so T of W is some scalar multiple lambda W for some scalar lambda. And if and only if, because if T of W is lambda W, then every scalar multiple of W is lambda times that scalar multiple. So you could think of it as sitting inside of your space. You have some one-dimensional subspace. Here's V. W is just all scalar multiples of W, and W is different from zero. It's a non-zero vector. And T of W is lambda W. And in this case, lambda is an eigenvalue of T with eigenvector W. So this says exactly what is an eigenvector and an eigenvalue. You have T from V to W, from V to V, and W different from zero. T of W is some scalar multiple of W. So if you have any vector in V such that T of W is a scalar multiple of that vector W, then the vector is called an eigenvector with eigenvalue T. And these are the simplest invariant subspaces. Now, not every linear operator has an eigenvector. So if you consider, suppose we let alpha be some angle, which is not a multiple of pi. So this is an angle in radians. And you can think of the linear transformation that takes every vector v and rotates it around. This is in the plane in R2. We have rotation by the angle alpha. If you take any vector v, this rotation, which I've called R alpha of v, sends v to what you get when you rotate it. And unless you're rotating by a multiple of pi, R alpha of v is not equal to lambda v. So v is different from 0. For all non-zero vectors, when you rotate the vector, you're not on the line through v. The one-dimensional subspace generated by v is just the line through the origin and the vector v, all scalar multiples of v. You rotate v by an angle alpha, you're off the line. So R alpha v is not equal to lambda v for all lambda. So therefore, rotation, the rotation operator, R alpha, has no eigenvector or eigenvalue. And because we're near the end of the term, I'm going to state various theorems about linear operators in general, but most of the examples will deal with the simplest case, where you have a linear operator T from R2 to R2. And with respect to a basis, T of any vector xy is given by a matrix A, B, C, D, X, Y, which is AX plus BY, CX plus DY. So the general, with respect to, if you pick that, say the standard basis, with respect to that basis, a linear operator in the plane from R2 to R2 is always uniquely determined by some 2 by 2 matrix. So what can we say about eigenvalues and eigenvectors for a linear operator T from R2 to R2 defined by T of xy is ABCD times the vector xy, which is AX plus BY, CX plus DY. So V xy not equal to 0, 0 is an eigenvector of T with eigenvalue lambda. This means that T of V is lambda V. Or if you like, T of xy is lambda times xy. What is this in terms of A, B, C, and D? T of xy is the vector AX plus BY, CX plus DY. Lambda times xy is just the vector lambda x lambda y. So V is an eigenvector with eigenvalue lambda if the coordinates of the x and y satisfy this vector equation, which is the same as, if you equate coordinates, ax plus by equals lambda x, cx plus dy equals lambda y. It means that you can solve this equation in x and y and lambda, where x and y aren't both 0. Let's see, if I write this in this standard form, ax plus by equals something. This is ax sorry, it says, I'm bringing everything from the right side to the left side. AX minus lambda x is A minus lambda x plus by equals 0. Cx plus d minus lambda y equals 0. So this is what? This is just two equations and two unknowns. This is a homogeneous system of two linear equations in two variables. And this system has a non-trivial, non-zero solution, that is, x and y not both zero, if and only if I look at the coefficients, a minus lambda b, c, d minus lambda, if I look at the matrix of coefficients, if this has a determinant, what is the determinant? AD minus BC. This is A minus lambda, D minus lambda minus BC. This is different from 0. This system has only the 0 solution. If this determinant is 0, then there's a non-trivial solution. So there's a non-zero solution of two equations and two unknowns, if and only if this is equal to 0. Which, if I just multiply this out, if and only if lambda squared minus a plus d lambda plus ad minus bc is equal to 0. So if and only if lambda is a root or a solution of this quadratic equation, it has to be a real root. Which is the case so long as the discriminant isn't negative. So if and only if ab squared minus 4 ac is greater than or equal to 0. This is just your high school algebra formula for how to solve a quadratic equation. And if this quadratic equation does have a real root or two real roots even, those are the eigenvalues. So let's look at an example. And this is exactly the type of problem that you will see in the homework and on the final exam. Suppose I take the matrix A to be 7, 4, 39. And I define the linear operator from R2 to R2 by T of xy is this matrix A times xy, which is 7, 4, 39 applied to xy. So we're looking at the quadratic, so lambda is an eigenvalue of t if and only if it's a root of the quadratic equation. What is the quadratic equation? Quadratic equation is lambda squared minus a plus d lambda plus ad minus bc equals 0. In this case, a is 7, b is 4, c is 30, and d is 9. So this equation is lambda squared minus a plus d, 7 plus 9 is 16, plus ad minus bc is 7 times 9 minus 4 times 30 is 63 minus 120 is 57. Plus 57 equals 0. Check this. A plus D. Oops. A plus D is 16. And AD minus BC, oh, minus there. That's good. Minus 57 equals 0. So we have to solve this quadratic equation. I notice that 57 is 3 times 19. So this factors into lambda 57 minus 19, lambda plus 3 equals 0. Because if you check, multiply it out, this is what you get. So the roots are, or the eigenvalues, are lambda equal 19, lambda equal minus 3. So this linear operator has eigenvalues 19 and minus 3. We need to compute the eigenvalues. Sorry, we found the eigenvalues. We need to compute the eigenvectors. So suppose we take lambda equal minus 3. We want to find a vector v equal to xy such that t of v is minus 3 times v, or t of xy is minus 3 times, or t of xy is minus 3 times xy. T of xy, what is t of xy? T of xy is 7, 4, 39. Xy is 7x plus 4y, 30x plus 9y. And we want that to be equal to minus 3 times xy, which is minus 3x minus 3y. So 7x plus 4y equals minus 3. 30x plus 9y equals minus 3y. So this is minus 3x. So this is the same as 10x plus 4y equals 0. 7, 4, 39. 7x plus 4y, 30x plus 9y, minus 3x minus 3y. So this is 10x plus 4y equals 0. 30x plus 12y equals 0. This is the same as, let's say, 5x plus 2y equals 0. Both of the equations are equivalent to this. So y is minus 5 over 2x. So I can take the vector v to be x, and y is minus 5 over 2x, which is, if I factor out an x, I get 1 minus 5 halves. Or if I factor out, since I always try to avoid fractions, x over 2, a half, 1, sorry, 2, if this is a half times 2, 2 minus 5. So for any x, so in particular, so let's just check. So 2 minus 5, check. what is A applied to the vector 2 minus 5? This is, let me do it on where I have some room. T of xy is 7x plus 4y, 30x plus 9y. So t applied to the vector 2 minus 5 is 7 times 2 plus 4 times minus 5, 30 times 2 plus 9 times minus 5. This is 14 minus 20 is minus 6. This is 60 minus 45 is 15. And by the magic of arithmetic, this is minus 3 times 2 minus 5. So t of 2 minus 5 is minus 3 times 2 minus 5. So this says instantly that we did it right. T of this vector is minus 3 times the same vector. So this is my eigenvalue, lambda, and 2 minus 5 is an eigenvector for that eigenvalue. So this is the case where lambda is minus 3. The other eigenvalue was lambda equal to 19. So in that case, 7x plus 4y, 30x plus 9y has to be 19 times xy, or 19x, 19y, which is the same as so 7x plus 4y equals 19x, 30x plus 9y equals 19y, which is the same as minus 12x plus 4y equals 0, 30x minus 10y equals 0. Both of these equations are the same as minus 3x plus 4y equals 0, or y equals 3x. So my eigenvector should be any vector of the form x 3x, or x times the vector 1, 3. So suppose I take this is my second eigenvalue, lambda 2 is 19, and I think that v2 equal 1, 3 is an eigenvector with eigenvalue 19. So let's check. T of the vector 1, 3 is 7 times 1 plus 4 times 3 is the first coordinate. 30 times 1 plus 9 times 3 is the second. 7 plus 12 is 19. 30 plus 27 is 57. This is exactly 19 times the vector 1, 3. So T of 1, 3 is 19 times 1, 3. So this checks. So we have for the eigenvalue lambda 1 equal to negative 3, the eigenvector v1 equal to 2 minus 5, for the eigenvalue lambda 2 equal 19, the eigenvector v2 equal to 1, 3. And we can also observe that the eigenvectors 2 minus 5 and 1, 3 are linearly independent. So B equal 2 minus 5, that vector, and the vector 1, 3 is a basis for R2. And with respect to this basis, the matrix for T with respect to this basis, the vector 2 minus 5 gets sent to minus 3 times 2 minus 5. So this is minus 3, 0. The vector 1, 3 gets sent to 19, 1, 3. So the second vector gets sent to 19. So with respect to this basis of eigenvectors, the matrix for T is a diagonal matrix. And diagonal matrices are really the simplest matrices there are. It's worth taking a look at this, so if you like, geometrically. We have V1 is the vector 2 minus 5. V2 is the vector 1, 3. So in the plane, the vector 1, 3 is there. This is V2 is the vector 1, 3. The vector 2 minus 5 is here. This is V1 equal 2 minus 5. So here we have two vectors in the plane. They're not perpendicular or orthogonal. Their dot product isn't 0. But they are linearly independent, and they form a basis. And with respect to this basis, the vector V1 has eigenvalue minus 3. It gets sent to somewhere up there. The vector V2 has eigenvalue 19. It gets sent to some other point up there on the same line. But with respect to this basis, the basis vectors are just stretched. The matrix for T with respect to this basis is minus 319. Diagonal basis is very easy to calculate. So if you take any vector V and you write the coordinate vector of V with respect to the basis B, let's say it has coordinates UV, then the operator T, so then if I take T of V, and I want to know what are its coordinates with respect to the basis B, I take the matrix for T with respect to B times the matrix for V with respect to B. That's minus 3, 0, 0, 19 times UV. This is just minus 3U, 19V. So this vector UV, the first coordinate is stretched by a factor -3. The second coordinate is stretched by a factor 19. It really is a very, very, very simple way to understand how this matrix operates. And the fact that the vectors, the two eigenvectors, were linearly independent is a consequence of the following fact, or the following observation. Suppose that T from V to V be a linear operator. Let lambda 1 and lambda 2 be distinct eigenvalues of T. Distinct means lambda 1 is different from lambda 2. And let V1 and V2 be eigenvectors for lambda 1 and lambda 2, respectively. So this means that T of V1 is lambda 1 V1, and T of V2 is lambda 2 V2, and V1 and V2 are non-zero. By definition, an eigenvector must be a non-zero vector. Claim lambda V1 and V2 are linearly independent. So what is the proof of that? So we have T of V1 is lambda 1 V1. T of V2 is lambda 2 V2, and lambda 1 is different from lambda 2. Suppose some linear combination C1 V1 plus C2 V2 is equal to 0. I must show C1 and C2 equals 0. That means that's linear independence. But T of C1 V1 plus C2 V2, T is a linear transformation. This is C1 T of V1 plus C2 T of V2. T of V1 is lambda 1 V1, and T of V2 is lambda 2 V2. But this is the zero vector, and T of the zero vector is the zero vector. So we have C1 lambda 1 V1 plus C2 lambda 2 V2 is the zero vector. If I take this equation and multiply this by lambda 2, I get C1 lambda, I multiply it by lambda 2, C1 lambda 2 V1 plus C2 lambda 2 V2 is also the zero vector. If I subtract, these cancel, I get C1 lambda 1 V1 minus C2 lambda 2 V1 is 0 minus 0 is 0. But this is what? This is this is C1. C1 lambda 1 V1 minus C1 lambda 2 V2. This is lambda 1 minus lambda 2 C2 V1. So lambda 1 minus lambda 2 C1 V1 is the zero vector. But lambda 1 minus lambda 2 is not 0, because lambda 1 is different from lambda 2. And V1 is not the zero vector. The only time a scalar times a vector is 0 is when the scalar is 0. So lambda 1 minus lambda 2 times C1 is 0, but this is different from 0, so C1 is 0. And if C1 is 0, C1 V1 plus C2 V2 is 0, means C2 V2 is the zero vector, which means C2 equals 0. So the only linear combination of V1 and V2, which is 0, is the trivial linear combination. So V1, V2 are linearly independent vectors. So here we have a 2 by 2 matrix, which has two distinct eigenvalues, and the corresponding eigenvectors form a basis, which is a very nice situation. But again, that doesn't always happen. Let me see if I can come up with an example where it doesn't happen. Suppose I take A to be the matrix 1, 1, and B to be the matrix minus 1. So my corresponding linear transformation T of xy is 1 minus 1, 1, 1 applied to the vector xy. That's x minus y, x plus y. And we want to know, does this linear transformation have an eigenvalue? So we can do this in two ways. First of all, we can look at the quadratic equation, which is, remember, it was lambda squared minus a plus d lambda plus ad minus bc equals 0. In this case, a, c, and d are 1, and b is minus 1. So we get lambda squared minus 2 lambda plus ad, which is 1. bc is minus 1, so 1 minus 1 plus 2 equals 0. We have to solve this quadratic equation. Well, we know from high school that the roots are lambda is minus minus 2 plus or minus the square root of minus 2 squared minus 4 times 1 times 2 over 2. This is 2 plus or minus 4 minus 8 over 2, which is 1 plus or minus square root of minus 2. This is not real. This is a complex number. So there's no real solution. So this linear transformation has no eigenvalue. We would see the same thing if we tried to solve this directly. Suppose we wanted to solve this is equal to lambda times xy, or lambda x lambda y. So we would be trying to solve the equations x minus y equals lambda x, x plus y equals lambda y. This is the same as saying 1 minus lambda x equals y, x plus 1 minus lambda y. Sorry, 1 minus lambda x minus y equals 0. Well, actually, that could be replaced. Same as 1 minus lambda x equals y. This says that x plus 1 minus lambda y equals 0, or x equals minus 1 minus lambda y, which is minus 1 minus lambda, and y is 1 minus lambda times x. So this is equal to minus 1 minus lambda squared x. So x plus, see, something here doesn't look right. X minus y is lambda x. X plus y is lambda y. So 1 minus lambda x minus y equals 0, or 1 minus lambda x equals y. X plus 1 minus lambda y is 0. So x, from this, x equals minus 1 minus lambda y, which is lambda minus 1y. This says y equals 1 minus lambda x, which is 1 minus lambda times lambda minus 1y, which is 1 minus, what is this? This is minus 1 minus lambda squared y. So 1 plus 1 minus lambda squared y equals 0. This is 1 minus 2 lambda plus lambda squared plus 1. This is lambda squared minus 2 lambda plus 2 y equals 0. Well, we got the same quadratic equation. This has no, this is never equal to 0, so y has to be 0. And if y is 0, then x is 0. So if all I'm doing is a simple calculation to see if there's a vector xy where t of xy is lambda times xy for this matrix or this linear transformation, and there's not. So there's no eigenvalue. So this is just an example of a linear transformation that has no eigenvalues. In some sense, they're bad. Now, but that raises the question, when does a linear operator T from a finite dimensional vector space to itself over the vector space over the reals have an eigenvalue, even 1, and more importantly, when does a linear operator have a basis of eigenvectors? So we have vectors v1 up to vn, and such that t of vi is lambda I vi for all I going from 1 up to n. And in that case, the matrix for t with respect to this basis called v is just the diagonal matrix with the eigenvalues down the diagonal. That really is a nice case, because you have linearly independent vectors, that is, vectors pointing in different directions, that are a basis for your space, and the linear operator simply stretches each of them. And there is a very nice answer to this question. So for this question, which is the important question, is if the matrix for T with respect to the standard code A, the matrix for T with respect to the standard basis, or with respect to any orthonormal basis. Remember what an orthonormal basis is? You have n vectors v1 up to vn, and the inner product of vi and vj is the Kronecker delta delta ij, which is 1 if I equals j and 0 if I is not equal to j. So you have a basis where every vector has length 1 and they're mutually perpendicular. So if the matrix for T with respect to any orthonormal basis is symmetric, this is the magic word. It's one of 2 magic words, is symmetric, then I'll just say yes. There is then there is a basis of eigenvectors for your vector space. What does symmetric mean? Remember, the transpose of an m by n matrix A is A superscript T for transpose, where Aij, the ijth component of the transpose is the jith component of A. So if A is m by n, A transpose is n by m. For example, if A is the matrix 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix, then the transpose, you're transposing rows and columns. If the first row of A is 1, 2, 3, the first column of A transpose is 1, 2, 3. If the second row of A is 4, 5, 6, the second row of A transpose is 4, 5. The second column is 4, 5, 6. This is a 3 by 2. And for a square matrix, we have 5, 7, 0, 2, minus 1, 8, 3, 10, minus 11. If that's A transpose is still a square matrix, still 3 by 3, but the rows become the columns. And A is symmetric. An n by n matrix is symmetric if A transpose equals A. So, for example, let's take the matrix A to be 1, 2, 2, 3. This is symmetric. The first row equals the first column. The second row equals the second column. This is 2 by 2, symmetric. So our associated linear operator, T of xy, is 1, 2, 2, 3 applied to xy. That's x plus 2y, 2x plus 3y. How do we find the eigenvalues? The eigenvalues are roots of the quadratic equation. Lambda squared minus a plus d lambda plus ad minus bc equals 0. For this matrix, A is 1, B and C are 2, D is 3. So this is lambda squared minus 4 lambda plus 3 minus 4 minus 1 equals 0. That's a quadratic equation. What are the roots? Lambda is minus 4 plus or minus the square root of minus 4 squared minus 4 times minus 1 over 2. This is 4 plus or minus root 20 over 2. This is 2 plus or minus square root of 5. I assume everyone can solve a quadratic equation, or you shouldn't have gotten to linear algebra. So what are the eigenvectors and eigenvalues? So for eigenvalue lambda 1 equal to 2 plus root 5, we want to have T of xy, which is x plus 2y, 2x plus 3y equals 2 plus root 5 times xy, which is 2 plus root 5 x, 2 plus root 5 y. So x plus 2y has to equal 2 plus root 5x, or if I subtract x from both sides, 1 plus root 5 times x equals 2y. So y is 1 plus root 5 over 2x. So xy is any vector of the form x 1 plus root 5 over 2 times x, which if I factor out an x, even if I factor out this 2 times x over 2 times the vector 2, 1 plus root 5. So for my linear transformation, t of xy equals x plus 2y, 2x plus 3y. Let me just check that this is an eigenvector with the right eigenvalue. What is t of 2, 1 plus root 5? T applied to this vector. This is x plus 2 times this. This is 2 plus 2 times 1 plus root 5. This is 2 times 2 plus 3 times 1 plus root 5. 2 plus 2, this is 4 plus 2 root 5. This is 4 plus 7 plus 3 root 5. Huh. What is that? Let's see. 2 times 2 plus root 5 is 4 plus 2 root 5. And 1 plus root 5 times 2 plus root 5 is equal to 7 plus 3 root 5. So what we have here is 2 times 2 plus root 5, 1 plus root 5 times 2 plus root 5. This is 2 plus root 5 times 2, 1 plus root 5. That is, t of this vector is 2 plus root 5 times the vector. So everything checks. I have, this is my lambda 1, 2, 1 plus root 5. Where my eigenvalue, lambda 1, is 2 plus root 5. So, yeah. Let's find the second eigenvalue. Or sorry, the second eigenvector. The second eigenvalue was lambda 2 equal to minus root 5. So now I want to solve the equation t of xy, sorry, t of xy, which is x plus 2y, 2x plus 3y, is 2 minus root 5 times x, 2 minus root 5 times y. If we equate coordinates, we get this equals this, which means 2y equals 1 minus root 5x. The second equation is 2x plus 3y equals this. So 2x equals minus 1 minus root 5 times y, which is minus 1 plus root 5 times y. 2 is the same as 1 plus root 5, root 5 plus 1, root 5 minus 1. Times minus. So this is the same, this equation is the same as this. So y is 1 minus root 5 over 2 times x. So solution xy is x 1 minus root 5 over 2 times x, which is the same as the scalar x over 2 times 2, 1 minus root 5. So I believe, if this is correct, that my eigenvector v2 is 2, 1 minus root 5. I want to check, and this is correct. And what is, and v1, what was v1? My first eigenvalue was 2, 1 plus root 5. And if I take the inner product of v1 and v2, that's 2 times 2 plus 1 plus root 5, 1 minus root 5. That's 4 plus 1 minus 5 is 0. So in fact, in this case, v1 and v2 are not only a basis for R2, but these two vectors are orthogonal. So let me just summarize what we've seen in this case. We have a symmetric matrix A equal to 1, 2, 2, 3, or the symmetric operator T of xy equals x plus 2y, 2x plus 3y. We have eigenvalues. Lambda 1 equals 2 plus root 5, and lambda 2, 2 minus root 5, and corresponding eigenvectors, v1 equal to 2, 1 plus root 5, and v2 equal to 1 minus root 5. And these are orthogonal. The inner product of v1 and v2 is 0. But the length of v1 is the square root of the inner product of v1 with itself, which is the square root of 2 squared plus 1 plus root 5 squared, which is the square root of 4, this is plus 6, 10 plus 2 root 5. The length of v2, if I take the inner product of v2 with itself, that's the square root of the sum of the squares of the coordinates, 2 plus 1 minus root 5 squared, which is the square root, this is 6 plus 4 is 10, minus 2 root 5. And if I let E1 be the vector v1 divided by its length, and E2 be the vector v2 divided by its length, these vectors are now orthonormal. So for this symmetric operator or this symmetric matrix, we have an orthonormal basis for the vector space, which is always very, very nice. And the matrix for T, with respect to this orthonormal basis, will be diagonal with the eigenvalues along the diagonal, namely 2 plus root 5, 2 minus root 5. So this is the story. So this is a story not just for R2, but let me just emphasize this. Let me just state this again. So we're not going to prove this theorem because it would take a lot of lectures. But I will give this theorem a star, that V be a real vector space, real inner product space, so real inner product space. In fact, we can just suppose it's n-dimensional Rn. Every symmetric linear operator T from V to V has an orthonormal basis of eigenvalues. Computing them can be hard, but they exist. Now, I want to understand symmetric matrices or symmetric operators in a better way, if you like. Let's just say, suppose V is an inner product space, and T from V to V is a linear operator. We say, so there is a linear operator, call it T star from V to V, such that for all vectors V and W in V, if I take T of V, inner product with W, that's the same as V times the inner product of T star with W. So if I have the inner product of T of V and W, I can like move the T over, but it becomes a different operator, T star. Actually, let me just call this S, so I don't have too many T's floating. And I want to describe S. So suppose we have E1 up to En, well, that's script E, that this be an orthonormal basis for the vector space V, and let the n by n matrix A, Aij, an n by n matrix, it's the matrix for T with respect to this basis E. So T of every basis vector Ej is summation Aij Ej, Ei, I goes from 1 up to n. That's the definition of, for the construction of the matrix for a linear transformation with respect to any basis. In this case, it's going to be an orthonormal basis. Suppose we let S from V to V be the operator with basis let me just call it Bij. So I have T from V to V. T of Ej is summation Aij Ei. I goes from 1 up to n. So what is the inner product of T of Ej and Ek? For any basis, so Ej and Ek are vectors in the orthonormal basis for T. This is the inner product of summation I goes from 1 up to n, Aij Ei, inner product with Ek. By the bilinearity of the inner product, this is summation I goes from 1 up to n, Aij, summation, Aij, inner product of Ei and Ek. This is summation I goes from 1 up to n, Aij, delta Ik. Oops, this one. Ei Ek, delta Ik. Because Ei Ek is 0 if I is different from k, and 1 if I equals k. This is the Kronecker delta. Which we've seen enough times now that we're supposed to remember it. So this is 0 unless I equals k. So this is A sub kj. That's what this inner product is. Suppose we let S correspond to a matrix. Let me call it Bij for the moment. So S of the vector Ek is summation Bik Ei. I goes from 1 up to n. So what is the inner product of Ej and S of Ek? That's the inner product of Ej and summation I goes from 1 up to n, Bik Ei, which is summation I goes from 1 up to n, Bik, inner product, Ej and Ei, which is summation I goes from 1 up to n, Bik, delta Ji. This is 0 except when I equals j. So this is B sub jk. So we have that T of Ej, inner product with Ek, is the inner product of Ej and S of Ek, if and only if Akj equals Bjk, means if and only if Bjk is Akj transpose. If and only if S is the transpose of T. So what we just proved is the inner product of T and Ej, T of Ej with Ek equals the inner product of Ej with the transpose of T applied to Ek. And T sub T is called the adjoint of T. And the matrix T is self-adjoint if and only if T equals T transpose, or if and only if T is associated with the matrix A equal Aij, if and only if A equals A transpose, or A is symmetric. So the bottom line is that if A is a symmetric matrix, then the inner product of A of V and W is V, the inner product of A, V, and A of W for all V and W in my vector space. So a symmetric matrix is the same as a self-adjoint matrix. So symmetry of a matrix simply means that if you reflect it through its main diagonal, you recover the original matrix. And a self-adjoint matrix has the property that for any vectors V and W, inner product of A with V with W is the same as the inner product of V with AW. Since the inner product is symmetric, that's what you can also say the inner product of AV with W is the same as the inner product of AW with V. And self-adjoint matrices or symmetric matrices by the big theorem always have an orthonormal basis of eigenvectors. You have a full complement of eigenvectors. And for symmetric matrices, vectors with distinct eigenvalues are orthogonal. Let us suppose T is a linear operator from V to V. T of V1 is lambda 1 V1. V1 is a non-zero vector with eigenvalue lambda 1. T of V2 is lambda 2 V2. If lambda 1 is different from lambda 2, then the inner product of V1 and V2 is 0. So this is, if you like, a theorem, but I can prove it. Of course, the proof is very short. We have lambda 1 times the inner product of V1 with V2. That's the same as lambda 1 V1 inner product with V2. Lambda 1 V1 is T of V1 inner product with V2. Because T is symmetric or self-adjoint, this is the same as the inner product of V1 with T of V2. But T of V2 is lambda 2 V2. To take out the lambda 2, this is lambda 2 V1 V2. So I have lambda 1 V1 V2 equals lambda 2 V1 V2. If I subtract, I get lambda 1 minus lambda 2 times the inner product of V1 and V2 is 0. The lambda 1 is different from lambda 2. So this is non-zero. I can cancel it. So V1 and V2 have inner product 0. So for a symmetric or self-adjoint operator, two vectors with distinct, two eigenvectors with distinct eigenvalues. Okay. Now, it turns out there's a very interesting way, given any matrix, not even necessarily square, just a rectangular matrix, to construct a symmetric matrix. So I have actually I should state the following two things. So first, maybe even as a little theorem. Let's say A is an m by n matrix. And B is an n by n matrix. So if I take A plus B, they have the same shape, so I can add them. The transpose of A plus B is A transpose plus B transpose. The transpose of the transpose is the original matrix. If, let's say, A is m by n, and B is n by p, then AB is an m by p matrix. A transpose is n by m. B transpose is p by n. So B transpose A transpose is p by m. A B transpose is p by m. And transpose is sort of anti-commutative. If I take AB and transpose it, that's B transpose times A transpose. So 1, 2, 3 are basic properties of the transpose of a matrix. And the fourth property is that if A is m by n, then A transpose is n by m. So if I take A times A transpose, that's an m by m matrix, and this is symmetric. Always. So a matrix times its transpose is always a symmetric matrix. And I can give a very simple proof of this. Symmetric means the transpose of the matrix is itself. So if I take A transpose, and I transpose that by the anti-commutative property, this is the transpose of the transpose times A transpose. But the transpose of the matrix A is just A. So A transpose is A transpose. That's the proof. Let me look at an example. Let me just start with a 2 by 2 example. Suppose I take A to be, 1, 2, 3, 4. So A transpose is 1, 2, 3, 4, like that. What is A transpose? That's 1, 2, 3, 4. 1, 2, 3, 4. This is the transpose of this. When I multiply them, I get 1 plus 2 is 5. 3 plus 8 is 11. 3 plus 8 is 11. 9 plus 16 is 25. This is symmetric. If I take A transpose A, that's 1, 2, 3, 4, 1, 2, 3, 4. That's 1 plus 3 is 10. 2 plus 12 is 14. 14. 4 plus 16 is 20. This is also symmetric. So A transpose and A transpose A, they're not the same matrix, but they're both symmetric. And therefore, each of these matrices has an orthonormal basis of eigenvectors. Now, in practice, it is very hard to compute eigenvalues and eigenvectors. And there is another theorem which turns out to be much more useful and is very used now in industry and Wall Street and lots of business applications, which is the singular value. So an eigenvalue is, we know what that is, but there's something different from eigenvalues, called singular values, and every matrix has a singular value decomposition. Let me just state what it is. Suppose we have A is not even necessarily a square matrix, an M by N matrix. So A corresponds to a linear transformation from Rn to Rm, right? Take a matrix, M by N times a vector, n-dimensional vector, you get an m-dimensional vector. Or say A from V to W, where dimension of V is n, dimension of W is n. So the rank, let me use T for the linear transformation. The rank of T is the dimension of the image of T. So remember the big theorem we proved some time ago. We have V and W, and T, a linear transformation from V to W. Sitting inside of V, you have T of V, or the image of V. And we proved the big theorem that the dimension of the image of V plus the dimension of the kernel image of T, dimension of the kernel of T, that's everything that just gets sent to 0, is the dimension of V. Dimension of the image of T is called the rank. So suppose R is the rank of this linear operator, there exist orthonormal bases V1 up to Vn for V, and W1 up to W sub m for W, and positive real numbers, sigma 1 greater than or equal to sigma 2, equal to the greater than sigma r greater than 0, such that T of Vi is sigma I Wi, for I going from 1 up to R, T of Vi is 0, for I going from R plus 1 to N. So if you were to write the matrix for T, it would look like sigma 1 down to sigma R, down the main diagonal, and zeros everywhere else. So we have V and W, and not necessarily of the same dimension, an arbitrary linear transformation T from V to W. And the singular value decomposition says that there are positive numbers, sigma 1 up to sigma R, which are unique. The bases are not unique, but the positive numbers, these singular values, are unique, such that sigma Vi is sigma I Wi, for I going from 1 to R. So that really is an important theorem, but the semester in the summer is short, and I might give an example tomorrow of how one computes such a thing. The proof is based on the symmetry of the matrices A transpose A and A transpose. So A transpose A is n by n, A transpose is m by m. For each of these symmetric matrices, there are orthonormal bases of eigenvectors, and those are the bases that go into this thing. but I'll mention that tomorrow. There's a lot this week to do, but the final is on Thursday. So I think the fundamental thing about eigenvalues you have to know is to understand eigenvalues and eigenvectors for 2x2 matrices and how to compute them. And that really will be as far as the final exam on Thursday goes. The final exam it'll be just like the midterm. It'll be on Thursday. I forget what time, either 2 to 4 or 4 to 6. If you have a conflict, if you tell me you have a conflict and what it is, then we'll arrange another time on Thursday. But it's a 2-hour exam, just the way the midterm is a 2-hour exam. Okay. That is it for the morning.